The heat waves are gone. The headlines have moved on. But deep in the North Atlantic, something far scarier than any record-breaking summer is quietly unfolding, and the scientists who study it are not relieved, they're terrified. For weeks this year, Europe baked under temperatures that shattered records set just months earlier. Germany hit numbers it had never seen. Spain crossed the mid-40s. The UK broke its June record 3 days in a row. Then, almost as fast as it arrived, the heat broke. Rain came. Temperatures normalized. Most people exhaled and went back to their lives. But behind that relief, a much older, much slower signal kept moving through the ocean, one that never made the news, and one that climate scientists have been quietly flagging as the real long-term danger. That signal is called the AMOC, the Atlantic Meridional Overturning Circulation. And if you've never heard of it before, you're about to understand why researchers care about it more than a single hot summer. Think of the AMOC as the planet's conveyor belt. Warm water travels north along the surface of the Atlantic, cools down near Greenland and the Arctic, sinks because it becomes denser, and then flows back south along the ocean floor. This loop has been running for thousands of years, and it does something no single weather event ever could. It moves heat around the entire planet. It keeps Western Europe far warmer than it should be at that latitude, and helps regulate rainfall patterns from West Africa to the Amazon. It is, in a very real sense, one of the load-bearing walls of the global climate system. And multiple studies published this year suggest that wall is cracking. Researchers tracking the Rapid Mooring Array at 26 degrees north, one of the longest-running direct measurement systems for the AMOC, found a decline of roughly 2.6 sverdrups per decade between 2004 and 2023. In plain terms, the current has weakened from about 20 sverdrups down to around 15. That's not a rounding error, that's a meaningful drop in the volume of water being moved by one of the ocean's most important systems. Separately, scientists studying the age of deep ocean water, essentially how long it's been since a given parcel of water touched the surface, found evidence that this weakening trend may have started even earlier than the direct measurements suggest, with the signal moving southward from the North Atlantic over time. That detail matters because it means this isn't a sudden blip. It looks like a slow-building trend that's been running for decades. Now here's where it gets genuinely uncomfortable. A 20-year measurement record sounds long to us, but for something like ocean circulation, it's barely a snapshot. Scientists studying the AMOC have openly admitted that even 2 decades of rapid data isn't quite enough to say with total certainty how much of this slowdown is natural variability and how much is a direct response to human-caused warming. That uncertainty isn't comforting, though, because the mechanism behind the concern is well understood, even if the exact timeline isn't. As the planet warms, ice melts, fresh water pours into the North Atlantic, and that fresh water is lighter than salty ocean water. It doesn't sink the way it needs to for the conveyor belt to keep turning. Less sinking means a weaker pull on the whole system. Weaker pull means a slower current, and a slower current means less heat being redistributed the way it has been for millennia. Some newer modeling has tried to push back a little on the most extreme scenarios. One recent high-resolution ocean model found that even with strong Greenland meltwater input, the AMOC weakening this century might land toward the upper end of what earlier climate models projected, but not necessarily beyond it. And importantly, the changes appeared reversible on century timescales in follow-up experiments. That's a genuinely useful finding, because it pushes back against the idea of an irreversible point of no return arriving imminently. But reversible over centuries is very different from harmless in the meantime, and this is exactly why the scientific conversation right now feels split into 2 camps that are talking past each other. One camp, often represented in newer CMIP6 style climate models, argues the slowdown will be gradual, that a full collapse before 2100 remains very unlikely, and that panic isn't warranted. The other camp, backed by decades of direct ocean observations and reconstructed proxy records, argues the real-world data is already showing a weakening trend that many of those same models struggle to reproduce. In other words, the tools we use to forecast the future don't fully agree with what the ocean is doing right now, and that mismatch is precisely why researchers say this deserves more attention, not less. When your models and your direct measurements disagree about something this important, that's not a reason to relax. That's a reason to look closer. And the potential consequences, if the slowdown continues or accelerates, are not small. A weaker AMOC would mean less heat delivered to Western Europe, potentially cooling parts of the continent even as the rest of the planet warms, a strange and counterintuitive twist where global warming produces regional cooling in specific places. It would also shift rainfall belts, potentially disrupting monsoon patterns that hundreds of millions of people in West Africa and South Asia depend on for agriculture. Sea levels along the U.S. East Coast could rise faster than the global average because a weaker AMOC affects how water piles up against the coastline. And marine ecosystems that depend on nutrient cycling driven by this circulation could shift in ways that ripple through fisheries. People rely on for food and income. None of this is science fiction. It's the kind of slow-motion, background disruption that doesn't make for dramatic headlines the way a heat wave does, but compounds quietly over years and decades. This is really the core of why scientists are more unsettled by the AMOC signal than by the heat wave itself. A heat wave, however brutal, is a single event with a clear beginning and end. It breaks records, it makes headlines, and then the weather moves on. The AMOC signal is different. It's structural. It's not weather, it's closer to the plumbing of the entire climate system starting to shift. And once a system like that changes meaningfully, it doesn't just snap back the way a hot week eventually cools down. If you've been following our channel, you already know we like digging past the headline event into the quieter signal underneath it, because that's usually where the real story is sitting. And if that's the kind of deeper climate story you want more of, go ahead and like this video and subscribe. It genuinely helps more people see careful reporting instead of just the loudest headline of the week. What makes this moment particularly interesting scientifically is the disagreement itself. Recent peer-reviewed exchanges have shown researchers openly debating which older datasets should even be trusted, with some studies questioning whether certain historical reconstructions properly account for known gaps in ocean data coverage. That's not scientists being sloppy. That's the normal, healthy process of climate science, working through a genuinely hard measurement problem in real time, right in front of us. And when you see that kind of open public disagreement happening in preprints and journal comment threads throughout 2026, it's actually a signal that this topic has moved from a fringe concern to something the mainstream oceanographic community is taking very seriously. So where does that leave us? The heatwave record set this year will likely be broken again next year, and probably the year after that too, because background warming keeps pushing the ceiling higher every single summer. That part is almost mechanical at this point. More warming means more record highs. It's simple math layered on top of a warming baseline. The AMOC story is different because it's not just about how hot it gets, it's about whether one of the ocean's oldest and most important circulation patterns is starting to falter. Scientists aren't saying collapse is imminent. Most current research still points toward a slow weakening rather than a sudden shutdown before the end of this century. But slow weakening over decades is still a fundamental shift in how heat and rainfall move around this planet, and that's precisely the kind of change that reshapes coastlines, farming regions, and fishing economies long after any single summer's heat has been forgotten. The uncomfortable truth researchers keep coming back to is this: heat waves are loud, visible, and immediate. They dominate headlines because they're impossible to ignore while they're happening. The AMOC is quiet, slow, and largely invisible to anyone who isn't reading ocean mooring data or deep-sea tracer studies, and that's exactly what makes it more dangerous in some ways, not less. A threat you can feel gets addressed. A threat that only shows up in numbers on a research vessel's instrument panel can be ignored for years while it keeps building underneath everyone's attention. That gap between visibility and actual risk is where a lot of climate scientists say the real danger is hiding right now, and it's why this particular signal has quietly become one of the most closely watched numbers in ocean science today. We'll keep tracking this story as new measurements come in, because the honest answer right now is that nobody knows exactly how fast this trend continues, and anyone claiming total certainty either way isn't being fully straight with you. What we do know is that the ocean's own long-term record keeps pointing the same direction, and that direction is weakening, not strengthening. If you found this breakdown useful, subscribe so you don't miss the next update, because this is very much an ongoing story rather than a closed case. Let us know in the comments what you think is more concerning long-term, the visible heat we can measure every summer, or the invisible current running underneath it that most people have never even heard of until today. It also helps to understand why this particular ocean system got singled out as a tipping point candidate in the first place. Climate scientists talk about tipping points as thresholds where a small additional push causes a system to shift into a completely different state, one that doesn't easily reverse on human timescales. Ice sheets, coral reefs, and the Amazon rainforest get mentioned in this category constantly, and the AMOC sits right alongside them on most serious lists. What makes ocean circulation different from a heat wave is the physics underneath it. A heat wave is driven by short-term atmospheric patterns, a blocking high trapping hot air for a week or two. Once that pattern breaks down, conditions return to normal fairly quickly. The AMOC runs on an entirely different clock, driven by the density difference between warm, salty surface water and cold, deep water. Changing that balance requires either melting enormous volumes of ice or shifting ocean temperatures over years, and once it changes, restoring it isn't quick either. That's the mechanical reason a slow ocean signal worries researchers more than a fast atmospheric one, even when the atmospheric one is setting records on the evening news. There's also a historical angle that makes scientists pay closer attention here. paleoclimate records, built from ice cores and ocean sediment layers, show the AMOC has shut down or weakened dramatically before, thousands of years ago, during periods of rapid ice melt at the end of the last ice age, that triggered abrupt regional cooling in the North Atlantic, even as the broader planet was warming out of an ice age. That's not ancient trivia. It's the closest real-world evidence that this system can shift, dramatically once pushed far enough. Nobody claims today's warming will trigger an identical shutdown, but the fact that this system has crossed thresholds before means scientists take today's slow decline seriously instead of assuming the ocean will simply compensate on its own. There's also a practical reason this matters beyond academic debate. Coastal cities along the eastern United States, from Miami up through Boston, already deal with sea level rise from melting ice and warming water. A weakening AMOC adds another layer on top, because ocean currents help hold water away from certain coastlines, and a slower current can mean water piling up faster than average. In specific regions, planners working on multi-decade timelines can't wait for perfect certainty before adjusting flood models, which is why oceanographers keep stressing that policymakers should pay closer attention now, not later. None of this downplays the very real danger of heat waves themselves. People die during extreme heat events, and death tolls from recent European summers have been genuinely brutal. The human cost deserves every bit of attention it gets. But scientists studying the AMOC are making a different point about which threat is more likely to blindside us because it's harder to see coming. Heat waves show up on thermometers in real time and hospitals prepare. A weakening ocean current shows up on instruments most people will never check, quietly reshaping weather patterns a decade or two down the line in ways that feel disconnected from any single cause when they finally arrive. That mismatch between visibility and actual danger is exactly the kind of gap that catches entire societies off guard.